Recording in progress.
All right, everyone. In this video, I want to introduce the first of what will be many applications of integration. The one that we talk about today is going to be a specific application, finding the area between two curves. But what I want to discuss first, and sort of how I want to frame this whole conversation, is about a way of understanding the core integration idea, because once we understand that idea, we can begin to apply it to various applications and be able to integrate more interesting and wilder kinds of objects, not just an area under a curve. And so, just to highlight where we are right now, we now have seen a good number of ways to calculate indefinite integrals. And we can do this by using a lot of different integration techniques, right? Strategies for finding antiderivatives. And then as a result, we can find lots and lots of definite integrals by applying the fundamental theorem of calculus. So a definite integral was giving us an exact and precise area under the curve. And we can now find this exact and precise area under the curve by appealing to the fundamental theorem and finding an appropriate antiderivative, capital F, for the function we're looking at, usually our lowercase f. And then, of course, the fundamental theorem of calculus says our definite integral would become capital F of b minus capital F of a. So what I want to highlight here in this part of the video is that our understanding of area and its relationship with Riemann sums or approximate areas constitutes what could be called our core definite integral idea. And this is the idea that we're going to want to generalize. And this idea, simply put, is that integrals are limits of Riemann sums, meaning there is a process under which we take more and more and more rectangles. We take something called a limit, and the approximate area becomes the exact area in that limit. And so what exactly do I mean by this? Well, this core idea can be summarized in 2 points. The first is that area can be approximated via a sum of rectangular areas. So the exact area that we want, this would be the orange picture over here. So the exact area that we might want, that picture on the right, can be approximated by setting up a bunch of rectangles and adding up or summing those rectangular areas. So you could think of this as either of the pictures on the left. We're approximating the area with a bunch of rectangles all smushed together. Each of those rectangles has an area we can calculate, and it's of the form h of x, the height, times delta x, the width. And so we can calculate this area, this height times width, and we can add all of these up. The second point is the limit idea. And what I mean when I say this is that as the number of rectangles increases, the actual approximation gets better. So we can do the same process. We can create this approximate summation, but the approximate answer we get is closer to the true area. And we can see this in the picture up above, going from the picture on the far left to the picture in the middle. The picture on the far left has 5 rectangles. The picture in the middle has 10 rectangles. They're the same values A and B, but each rectangle is skinnier as we move to the middle picture. Each rectangle is skinnier. There are more rectangles, and the approximation is better. The over or under estimate is smaller, the error is smaller, and we are getting a better approximation for this true area. All right, so this sort of 1-2 punch forms the core idea in the definite integral, at the heart of definite integration. That we can approximate our area via a rectangular sum, and that as the number of rectangles increases, the approximation gets better. Usually, this is summarized in a formula, kind of like what's written at the bottom of the screen here. You'll notice that what we have is, I'll put it in blue parentheses here. Woof, that's a tough parenthesis. I'll put it in, oh my gosh, that's even worse. Let's try that one more time. We've got a parenthesis here, okay. What we see here is that this is the Riemann sum. It's a sum of n different areas of n different rectangles, each of which has the form height times width. What we see then is that if we take that approximation, if we take that summation, we get an approximate area. And as we increase the number of rectangles, and that's this piece out front, this limit as n goes to infinity, if we add on more and more and more rectangles, each of which are skinnier and skinnier and skinnier, we get a better and better approximation. And as we continue this process, we end up getting the definite integral, and that's this object over here on the right. This orange object over here on the right. Okay, great. So the core idea that I want to move to now is that we can begin thinking about this not just in terms of definite integrals for area under a curve, but in more general observations as well. Specifically, if we want to approximate not just any area, but some object, so the object of interest, again, this is still in this picture, this orange area, but if an object of interest can be approximated via a sum of, let's just say, a sum of expressions of the form h of x times delta x. So if it can be approximated via a sum of expressions in this form, and if as the number of I don't know, if the expressions h of x times delta x, if those numbers increase, maybe I'll just say as the delta x gets small, that's another way to think about this, is the widths are getting small. So as the delta x gets small and the number of objects we're summing gets large, the approximation gets better. So if we can create a framework like this, it doesn't have to be specifically area under a curve. It doesn't specifically have to be representing a rectangle. But if we can get an expression of the form h of x times delta x, and if that expression is an approximation, and if that approximation gets better as the delta x's get smaller, then we should be able to get an exact answer by converting from our approximate summation approach to an integration approach, as we see down here at the bottom. So that's sort of the big idea here. In essence, we're trying to ask what kinds of things can we approximate besides just area under a curve, between a curve and an x-axis. And can I set it up to look like an h of x times delta x? And can I make that approximation better and better by making the delta x smaller and smaller? And in doing so, maybe I can find an exact answer via integration. So that's our big idea here. What that means is that we're going to be developing a lot of theoretical frameworks involving approximating quantities that we care about, and then being able to compute those quantities exactly by taking an appropriate integral. And that's what a lot of the applications of integration are about. Let's conclude this video by looking at one example. Oh, and I should say, sorry, before we do that, I should just say this will be true regardless of which Riemann sum type we are looking at. So at this point, we've seen left endpoint Riemann sums, right endpoint Riemann sums, midpoint sums, and trapezoid sums. The truth is, any one of those is a perfectly fine summation to use in this richer theory. And so as long as we are getting an approximating sum of one of these four types, and as long as those approximations are getting better, we can use this structure, this conceptual structure, to help us calculate something via integration. Okay, so let's look at our one example. This is going to be the area between two curves. And we have the framework that's drawn here. I have roughly the same picture drawn 4 times. I'm going to focus on the upper left. I want to figure out this shaded purple area. It's between a function a and b, and it is the area between the function f of x and the function g of x. F of x is up on top, g of x is down below. And so specifically, what is that shaded purple area? Now, I'm not going to bury the lead here. There is a formula for this, and it's exactly as follows. We can take the integral from a to b. So this is an integration. We can calculate this via integration. It's going to be the integral from a to b, and it's just going to be the function f of x minus g of x dx. So we're going to take whatever our function x was, whatever our function g was, subtract the g from the f, and then integrate that function from a to b. And so that's what we get here. We can see this, or we can reason it out pretty quickly just by making the following observations. That if I wanted to calculate this total area, I'm going to sort of rush this picture. But if we want to calculate this total area, come on now. If I want to calculate that total area, that green area, is just the integral from a to b of f. And if I want to calculate a slightly different area, let's say in light green, I want to calculate this area. Right, then that's just going to be the integral from a to b of g dx. And so what is the purple area? Well, the purple area is literally just the entire big green area. Right, so the big green area was all of this. And then minus, there we go, minus the light green area. So the light green area was this area down here, the area under g of x. And so it's the big green area, or I should say the big dark green area minus the smaller light green area gives us exactly this purple area. So of course, we should end up getting, for that purple area, it should be the integral of f minus the integral of g, which can be written as the integral of f minus g. So of course, this is the right formula. This is what we expect to see here. But using the framework from up above, there's another way that we can think about this. That of approximating via rectangles and taking better and better approximations as the number of rectangles increases. So let's at least see theoretically how to do that. And I think I'm going to need some straight lines here, because otherwise my picture is going to be very rough. And so what we can do is we can take this area and let's just pretend, let's pretend this is a good picture and these are all nicely evenly spaced out. What I can do is I can take a bunch of rectangles that roughly look like this. Right, so I can approximate the area that I'm interested in using a bunch of rectangles. We're going to pretend, I'll zoom in here in a moment. In fact, here, I'll zoom in right now. We can pretend that all these rectangles are the same width. Of course, that didn't quite shake out. But each of these widths, let's say, is a width of delta x. And each of these rectangles has a given height. And what is the height of each of these rectangles? Well, the height of each of these rectangles, let me grab a dark blue here. The height of each of these rectangles is going to be, in a given rectangle, one of these heights. And that height can be interpreted as an f of x value. Let's pretend at this value here. So I'm just going to name this xi. So at this value, I'm calculating the function f at xi. and I'm subtracting the function calculated at g of xi. So this just becomes f of xi minus g of xi. And that gives us the difference between f and g at the point xi. And that is exactly the height of that particular rectangle, in this case, the third rectangle. But we get an expression then in which the rectangle that we're looking at, and I'll focus, again, I'll just sort of focus on one of these for now. That rectangle has a area of the form f of xi minus g of xi, that's the height, times delta x, that's the width. And so what's the whole approximate sum? What's the area of all these rectangles added together? It's just a summation as I goes from 1 to n. So we're adding up all n of these n different rectangles. And each of the rectangles has an area given by this form. Now, this is telling us we can approximate the purple area using this rectangular area. And it should also be believable. Like, you should look at this and believe that it's probably the case that if I made more of these rectangles and I made them skinnier, I would get a better approximation. More rectangles will better approximate this. And so what we see is that by taking, and again, we'll use this, this limit notation, by taking more and more and more rectangles of this form, we are going to get the exact purple area. And now let me zoom out and point to the fact that this limit expression, not only will it equal the purple area, but from the structure up above, I'm going to scroll back up. Maybe I scrolled too far. There we go. A limit of a summation of something that looks like an h of x times a delta x, that becomes an integral of h of x dx, right? So just looking at this piece right here. So scrolling back down, whatever I was summing between my summation sign and my delta x sign, that is what I will get in my integral down the road. So now we see that not only is this limit expression giving us a better and better approximation, and in the limit giving us the exact area between curves, we see that it is equal to the integral from a to b of f minus g dx. Because again, what I'm focused on is this piece in here between the summation and the delta x, and that becomes the thing that I integrate in the exact answer. So this is our new theory. Not only do we get a bunch of nice formulas allowing us to compute very specific things, like here we learned a formula to compute the area between curves, but we see this framework for creating the formula by setting up an approximation, recognizing that that approximation looks like a Riemann sum, and then recognizing that that Riemann sum type summation gets better and better and better as the number of rectangular-like pieces increases. So that's going to do it for this video. We'll see more of this down the road. Thanks so much for watching. See you next time.